Hello everyone. Today I'm going to continue my case study series, and this will be the second dataset. So the first thing, you need to download the dataset from the CCDC bit database, and after that you open in Olex2, and so the zip file you downloaded should be the all-included zip file. So that means it must have the HKL embedded. Okay, so the first, take a quick look at this panel, and here you see so many outrageous indicators. For example, the I1 value is so high, nearly 15, and WI2 is just huge, and the signal intensity is very weak. It's just 5, and I-inter is also too high. And so this tells me that this is a very weak data set and a very bad data set overall, because this zip file we wanted to convert it to the res file and HKL file, which we can refine independently. So we just click that refine. It will just extract the res file and HKL file, and to give a run of refinement. So what's taking so long? Okay, so I guess the also set up a very large cycle number. Yeah, no wonder this is 20, which is too big. You only 4 is good, and if it's not enough, just click refine again. So you really don't need to give this higher cycle numbers. And let's start with 10. Okay, let's refine one more time, just for the sake of finding out how long it will take for 4 cycles. Okay, it's not too bad. Okay, now if we click this icon, you bring up this F observe versus F calculate, and you can see this thing is just so noisy. And without looking into further details, I would, if I'm serving as a referee for the journal, I would definitely recommend this data not to be published. This data is just nearly garbage. See so many outliers, and it's not very tight. You can still see it's relatively linear, but its data quality is very, very low. I guess mainly because the raw data they collected from the instrument are very low quality. See, the intensity is I over sigma is barely 5. And you want this to be the higher the better. I have, with a modern instrument, it can easily get over like 50. So 5 is definitely too low. I would say you probably want it to be at the minimum around 15 and above. So this alone indicates the data is so bad, and plus with I-int, something is wrong with the raw data, definitely. Okay, so my intention is, given this bad data, what's the best outcome we can get? Okay, let's see if we can tweak around some parameters to make this data looks better. It may not be good enough to be published, but at least it will not appear so outrageous. Okay, so let's see, check a few reflection statistics. Okay, let's see the I over sigma versus I over sigma versus resolution. Okay, we want to see this. Okay, see this? The resolution when it's around 1, it's below 3 sigma line. So 3 sigma line is generally recommended that this is the minimum intensity of your data you want. So anything below this is very close to noise. So you don't want a hefty portion of your data to be below this 3 sigma line. And definitely you don't want your data to be below the 1 line. See this here? When the resolution is 0.855, the I over sigma is already close to 1. So that means the data quality the resolution here, really you cannot go down low. Okay, you probably at the best cut around 0.83. Okay, so and let's also see some band reflections. Okay, there are some band reflections that also did not take care of. And okay, without further ado, we want to see if we can improve this data set. Okay, let's just start our regular routine starting from the very beginning. Click solve. Click yes to confirm. You want to solve it and start from scratch. We will compare our final result with this here. Obviously, cannot improve the raw data, but it tweaks some parameter to make it look better. By the way, when I downloaded these save files from CCDC, I did not find the check save file, which is strange. I'm surprised that CCDC actually accepts this dataset without the check save. If you run a check save file, I bet you will see tons of alerts. This will definitely trigger a lot of alerts. Okay. With the reference structure in mind, we know what kind of structure we are looking for, and this doesn't look bad. See, there are only a few misassignment of atom type. For example, we know this is a central metal is nickel. We have 4 nitrogens coordinated with it. Then there is ring here with 2 nitrogens. So this one should be nitrogen, but this was not. So let's first correct this misassignment by changing the carbon to the carbon atoms. Okay, let's see. Let's click carbon to assign those back to carbon. And this is actually 2 chemically identical molecules, but crystallographically non-identical. That's why in the asymmetric unit it has 2 molecules. Okay, so then let's see. Yeah, this also has to be carbon. Then let's correct this to be nitrogen. And for this molecule, yeah, they are right. So next thing is Control R to refine. Okay, let's see. This is not too bad. Okay, so let's see. It has shifts and so many red areas. Let's see which ones. Okay, it's not the atom position, it's something else, but this flag number is 0.9, which is close to 1. Then it indicates absolute structure is wrong because this is a non-central symmetric space group, so it has polarity. So to invert the absolute structure, you need to type a command invert, then you add an argument with force. Basically, you force the program to carry out an inversion of this amplitude structure. Okay, just enter. Then you Control R to refine. Okay, now it takes effect. So basically, it's close to 0. If it's ideally 0, that means it's no problem. It's slightly away from 0, indicating there is some issue there. We will take care of that later. Let's refine one more round to see if it will settle down. I bet it will. Yeah, good. So next, let's check this real quick. Yeah, okay. Remember in the very beginning, we checked the Refinement statistics and we checked this one. We checked here, we want to make sure the intensity is above 1. So in this case, the data is so bad that we can see that below 0.83 resolution, the I over sigma is actually below 1, which means the signal is actually buried under the noise. So it's not contributed to your result positively. It's actually making everything worse. That's why I suggest a cutoff resolution value at 0.8, maybe 0.83. Okay, so the way to do that is just type edit to bring up this ins file, and anywhere find a line anywhere. Actually, the program will automatically rearrange the file, so doesn't matter where you put it, as long as it's above this, the atom list. So, for example, you put it here, start with shell, then from pretty much positive infinity to 0.83. This is the resolution shell. So just Control S to save this, close this, refine again. You notice the changes here, okay? See, all of a sudden, the I1 value drops, I inter value drops, I over sigma drops. The reason is because the original data contains a tons of noisy data. It is actually all purely noise. So you include so much noise in your data, it's not contributing positively to the calculation. It actually makes the statistic looks even worse. So I normally don't recommend people to cut off the data, even the weak data, but when it is below I over sigma below 1, you definitely should cut it, okay? If you have a very good, strong data, for example, let me just bring up this again. For example, the resolution, even it's very high resolution, like goes to 0.7, 0.6, or even 0.5, and all the I over sigma are still above this 3 sigma line, meaning it's green, then definitely do not cut those, okay? With those high angle data there, your structure tend to have a very good feature for the fine structures. Okay, you can probably even locate the proton with that type of data quality. But when the data is below 3 sigma, and if it's a hefty portion of that data are below 3 sigma line, that means the data quality is very bad, and you should start to consider to cut some of the data with this low low intensity, and especially when it's below 1, you definitely should cut it. It's not doing you any good. It's actually making everything worse. So with that being said, let's refine now. Okay, the shift is stabilized. And what we need to do next is convert this isotropic model to anisotropic. So you can just type anis, enter, Control R to refine. Okay, one more time. I think it should be there. Okay, it's not bad. So while it's refining, I want to show you this new indicator. I think it was added maybe a few months ago. This is the data to parameter ratio. So the higher this value, the better. I think the recommended value is 8. So in this case, it's okay. It's close to 10, which is acceptable. The only thing is I'm surprised this data is recently published. Either they have a very bad crystal or their instrument is very old. Whatever it is, this data quality is not acceptable. Next step will be to add a proton. So you can just, again, you click here, or you just type each add in the command line. Okay, let's see what is this shifting. Yeah, it's no one because the data quality is very low. There will no localized electron density here, so that program has to rotate this proton around to find the most comfortable position. In this case, shift is settled down, and if we examine this around. Generally speaking, the model looks fine because we have that reference model in mind, that we know what we are looking for. So it looks okay. And the next step is to just update the weight. So you check this box and refine. Okay, finally the weight settled down, the shift settled down. So this refinement is converged. And if we check here, most of the indicators are within spec. This orange are not good, but it doesn't look that horrible. And there are a few issues we might want to take care of. Of course, this I over sigma, there's nothing you can do because this is directly from the original data. You can cut off that weak data, whatever is I over sigma below 1 to make this statistic looks better. That is what I mentioned in my last video. I said you can play with some parameter to artificially lower this I1 value and even increase the I over sigma value. But again, ultimately it is your original data quality dictate the final quality of the refinement result. So basically, if it's good data comes in, you can get a good data outcome, but if it's garbage in, you get a garbage out. So I cannot stress enough that you have to spend enough time to get a very good data set. Okay, if you have a good data set to start with, you won't need to spend this much of trouble trying to make it looks better. Okay, in this case, I still don't recommend this to publish, but just trying to see if we can make it looks better. Okay, this experience will be useful for future. So here there are several things you want to look. First, it says contents from the unit instruction and item list do not agree. So you just update to the current one, and you want to see Z prime should be 2 because this is two of the chemically identical structures. So you should make Z prime equals 2. So Z prime is how many molecules are in the asymmetric unit. So in this case, there are 2 molecules in the asymmetric unit. So Z prime should be 2. You just okay. Then this will give you the chemical formula for one of the chemically unique structure. For example, if you want to just double click this, type unique, this is actually the chemistry structure you are looking for. So the next thing is the flank parameter is 0.044. So this value should be 0 theoretically, and when it is 0, there's nothing wrong. When it is 1, that means the absolute structure is just the inverse. So you have to invert the polarity. However, if it's anything between 0 and 1, then you need to take care of that. For example, if it's just 0.5, then that usually means you missed an invariant center. For example, if you have a P1 space group and you get a flank parameter of exactly 0.5, and in the ESD, the parentheses is very small, then that means you actually should have a central symmetric space group. P1 plus that flank parameter of 0.5, then it equals P1 bar, right? So it's a central symmetric space group. So, but if it's any number between 0 and 0.5, and the ESD in the parentheses is reasonably small. ESD has to be small to make a statistic significance. So if the ESD is very large, then that is because you don't have much of the anomalous scattering elements. For example, either use moly and you don't have a whole lot of heavy metals. Combined with that source is moly, so you are not going to get a very good anomalous scattering. In that case, if your structure is not a chiral, then you don't need to worry about that. If you if your structure is indeed chiral and you are interested to find that chirality by the X-ray method, so you need to switch to copper and try to get a higher redundancy and scan a high angle, then that will give you a more reliable flank parameter. More reliable means the ESD in the parentheses are very small. Okay. The next scenario is the flank parameter is 0.2 with a small ESD. In that scenario, it means your structure actually have invariant training there. So what you need to do is you need to account for that invariant training. Invariant training sometimes is also called rhythmic training. So the way to account for that is you just type edit, goes to the ins file, then add a line here, twin, then followed by the twin law, which is -1 0 0 0 -1 0 0 -1. So then you have a batch skew factor of really doesn't matter how much, but here since it is flank parameter is less than 0.1, so you just give a 0.1 here. So if in real scenario, if you have a 0.2 here, you should give a 0.2 to start with. Okay, so you just Ctrl S to save, then refine, and this flank parameter indicator will be gone because you actually use a tuning to account for this. So that indicator is gone. So in this real scenario, you may not need to use tuning to account for that flank parameter because one, that flank parameter is small enough. It's like a 0.0 something. Two, that ESD for that flank parameter is also big enough that makes this flank parameter statistically not reliable. So you actually can discard that. You don't need to care about that. Okay, so I think that's what we can do so far. And the final things, you want to check the band reflections or outliers. Let's check here first. Okay, see, this is a weak data we excluded by that shell 999.83. Basically, you omit all those reflections with I over sigma below 1. Okay, and here, this is a huge outlier. So just it's 112. You just ignore it safely. So you don't need to worry about that if you only discard a few outliers, as long as it doesn't show a pattern. Okay, this already looks a little bit better than the original one, but still not good enough. Just continue to refine until everything settles down. Okay, looks good. So I1 is now 11 point close to 5, and I want to bring up the original result from the CCDC so we can take a look. Let's see if I open here with that Olex2, and we put those two data sets, two final refinement side by side, and we want to compare which one is better. I mean, I already know, of course, this original data is not good, so with garbage in, you cannot get diamond out, right? Okay, now you compare side by side. So the I1 value is close to 15, this one is close to 12, so significantly lower, okay? Still not within spec. Ideally, you want this to be within 5%, and in some rare scenarios, you can justify your publication if it's close to 10% and below. But anything beyond 10% is not good. You can probably use this as a connectivity purpose, but the quality will not be good for you to discuss the bond angles or bond distance, etc. Then this I over sigma, artificially we raised it, but we just cut off the noisy data. Similarly, the int, because you remove those very noisy data, it makes statistic looks neater. And so we remove that flag parameter by accounting that effect with training. And everything else pretty much the same. And if you look at this f observe versus f calculated, and you can see they are generally very similar, of course, but these outliers are removed and together with this one. That are the major changes we made to make the indicators looks better in general. Okay, hopefully you guys learned something from this. If yes, please click like or leave a comment below. Let me know. Thank you very much for watching, and see you next time.